Right, this time do the Laplace transform. This one becomes s squared ys minus sy0 minus y prime of 0 plus 4 times sys minus y of 0 plus 13 ys. How about this one? What's the Laplace transform of that? E to the 2t. This is the case when n is 0, so it's 1 over s minus a, with a being 2. So what would you get? 1 over s minus 2. That's what you get. Okay. All right, since this is 0, y of 0 is 0, that's gone. That's gone. If I collect the y's's, it's s squared plus 4s plus 13 ys. The only survivor that doesn't have y of s in the left side is this one. And because that's 2, when you move it to the other side, it becomes 2 plus 1 over s minus 2. Okay, and then we divide both sides. And we get y of s equals to 2 over s squared plus 4s plus 13 plus 1 over s minus 2 s squared plus 4s plus 13. And again, in order to figure out what y of t is, we have to do the partial fraction expansion. Okay, notice that this cannot be factored. The best you can do is complete the square. This is s plus 2 squared. 2 squared is 4. 4 plus 9 is 13, so it's 9. Or you can rewrite this as 3 squared. And therefore, when you do the partial fraction expansion, you will need one of this, a over s minus 2. And then you will need another one for this one. Because this is second order, you would need b s plus d, c, plus s plus 2. Let me just rewrite this in this form. Okay. That's better. Okay. And I put bs plus c because this is the second order, so you need one less. However, we already have seen how hard it is to go back, even if you have the numbers, when you're trying to work with b's, right? So here's a strategy that I want you to use from now on. Okay, so this would be how you are taught to do the partial fraction expansion usually in Calc 2 when you learn the integrals. But because we have these in mind, I want to rewrite this one as, instead of bs, I'm going to write b of s plus 2. I want to write it as b of s plus 2 because then these two match, and these, it's exactly like this form. So once you get your b, then you can immediately transform, you can immediately find the Laplace inversion of that because this formula applies directly. So that's a shortcut. Writing instead of bs plus c, writing it as bs plus 2 plus c, and trying to find out the b and c this way will be a shortcut. Okay? Yes?
How are you capable of just doing that? Like, wouldn't that change?
So it's like this. It would change the value of c.
Okay.
Yeah, but it's exactly in the form that we want.
Okay.
Solving this question and solving the one with s plus 2 will give you different value for c. But even if you didn't have s plus 2, from that c you will have to shuffle things around again, just so that one side looks like this and the other side looks like a constant over that. So you will have to do more work. Okay. So all I care about is the fact that I'm able to say this is equal to the right side in this form for some a, b, and c. Okay. All I'm saying is that there is some bunch of functions whose sum is same as the sum of these functions. And they're equal as functions, meaning that they agree for all values of s. Okay. Now, in addition to this, I want to go even further. I want to say, since if it was like this one, I need this to be same as that, right? So I'm even going to rewrite this as 3c, or c times 3. Okay. Then once I get the number, then I will automatically have 3 over this, so I can easily do the inverse transform. Again, solving the one without the 3 and with the 3 will give you different values of c, but that's not my concern. As long as I know that this function is exactly same as this function, I know the inversion of this one, then that means I know the inversion of this. That's all I care. Okay? Does that make sense? All right. So now let's multiply this both sides. If I multiply to the first one, this will cancel with the denominator, and s minus 2 will survive. So I'm going to get 2 times s minus 2. This times this will give you just 1, because the denominators cancel. I'm multiplying this to all of these terms, okay? And a will be multiplied to what?
S squared plus 4s plus 3.
Remember, we decided to write this as this, okay? And then plus b times s plus 2 plus 3c times s minus 2. So that's what I want. Now we plug in s equals to 2, because then I have just 1. If s is 2, let's see, that's 4 squared, which is 16, plus 9, that's 25a. And then this one's 0, because if s is 2, 2 minus 2 is 0. So that immediately gives us that a is 1 over 25. Then I want s equals to negative 2, because if s is negative 2, then b goes away. So let's see, if s is negative 2, that's negative 4 times 2, negative 8 plus 1, negative 7. Negative 2 squared, negative 2 plus 2 is 0, so that's gone. That's 9a. And then negative 2 gets rid of b, and negative 4 times 3, so negative 12c. All right, that's very messy. Let's move this to the other side and put the 7 over here. So it's 12c equals to 7 plus 9a. So it's 9 over 25. 7 is 175 over 25. So that's 184 over 25. And dividing by 12, it gives you that c is 184 over 300. Because 12 times 25 is 300. So if you divide by 12, that's same as multiplying by 12 in the denominator, so you get 300 in the denominator. Okay, I guess you can divide top and bottom by 4. Should I? Let's do it. If I divide top and bottom by 4, the bottom is 75. Top is 4, and then 60, 24, 46. Okay, 46 over 75. That's your C. Now, we run out of good numbers to plug in. What's our next best thing to do?
First highest.
Highest order. See, on the right side, s squared is the highest order, right? This one doesn't have s squared, so if you just look at s squared, the left side is 0 times s squared. Whereas on the right side, you have as squared plus bs squared. So you see that a plus b should be 0, giving you that b must be negative a, which is negative 1 over 25. All right. Huh? A plus b must be 0, because a plus b times s squared should be 0 times s squared. So a plus b is 0. If you subtract a both sides, you get b equals to negative a. So b is negative 1 over 25. Okay? All right. So now we're almost done. Now we have that y of s, which was this function, it's equivalent to this other function, which was 1 over 25 times 1 over s minus 2, plus negative 1 over 25 times s plus 2 over s plus 2 squared plus 3 squared. I'm really splitting this into two fractions, one into this one, another into that one. Okay? You can split a fraction into this over that and plus this over that, right? Okay, so one is 3c, so I'm going to put the c outside. C is 46 over 75, so it's 46 over 75 times 3 over s plus 2 squared plus 3 squared. Okay? Everything good? Okay, hopefully I didn't make any mistake. Therefore, what's the answer? Answer. Y of t. This one means, what do you have in the original? E to the 2t. What gives this one? E to the negative 2t. It's this one, right? Right.
Plus.
It's the cosine. Cosine, what?
Of 3t.
Cosine 3t. 46 over 75 times e to the negative 2t
Sine of 3t.
sine 3t. Now, if you have time at home, try to redo this using the method of undetermined coefficients. You know how to do that, right? You write the yp as a times e to the 2t. Yc is something times this, something times that. You write down the general solution and then use the initial condition. You can find the same solution as this one. And I think the amount of calculation will be pretty much similar. It's not, that one is not better than this one. Any questions? Now, one thing I want to say is that when you're solving with Laplace transforms, it's comparable to method of undetermined coefficients for these things. But the reason that you are taught to use Laplace transforms is that Laplace transforms can solve a little more than what you're used to solving. So method of undetermined coefficients only allows you to solve if the right side is like easy 2t or sine 2t, cosine, or some polynomials. That's about it, right? For Laplace transforms, it can handle something called a Heaviside function. What's a Heaviside function? A Heaviside function is like it's 0 before and suddenly it jumps to 1. That's called a Heaviside function. Now this is useful in your electric circuits because the moment you press the switch, you want to know what's going to happen, right? And to model such a thing, you end up with a Heaviside function on the right side, and to solve that, you basically don't have any other choice than to use Laplace transforms. So in your engineering courses later, when you solve differential equations like this, you'll most likely be using the Laplace transform to solve it. That's why we're doing the Laplace transforms. All right, so let's have a quiz.